Structure of Matter by Colin Kong. How did we learn about atoms? The atom. Do you know what silver has in common with the helium in a balloon? They are both made up of tiny particles called atoms. An atom is the smallest whole piece of matter. Tiny atoms are joined together to make the structure of silver and helium. It is very difficult to study atoms because they are so small. Scientists have to use models to help picture an atom. This model has changed over the years as scientists gathered new information. Today, scientists use the electron cloud model. In this model, the atom has two regions, the nucleus and the electron cloud. The nucleus is found in the center of the atom. Protons and neutrons make up the nucleus. Protons are particles with positive charges. Neutrons have no charges. An electron cloud surrounds the nucleus. It contains the electrons and a lot of empty space. Electrons are particles with negative charges that move freely in the electron cloud. History of the atomic model. Scientists did not always know that atoms were made of smaller particles of protons, neutrons, and electrons. It took more than 2,000 years to develop today's model of the atom. A Greek philosopher named Leucippus first came up with the idea that matter is made of smaller particles. His student, Democritus, further developed the idea. He named the particles atomos, meaning indivisible. Democritus believed that atoms were hard solids that could not be destroyed. He also described them as being completely full, which meant that they had no empty space inside. Democritus also believed all atoms were made of the same material in many different sizes and shapes. Aristotle, another Greek philosopher, did not agree with Democritus's model. He believed that matter could be divided and subdivided indefinitely. Aristotle did not believe in atoms. He proposed that everything on earth was made up of a combination of earth, wind, fire, and air. Aristotle's theory was more popular than Democritus's theory. Many scientists challenged Aristotle's ideas, but their theories were also rejected. Among them were Galileo Galilei, 1564 to 1642, and Robert Boyle, 1672 to 1691. Who claimed that everything was composed of tiny but not indivisible particles. Aristotle's theory remained popular until the 1800s. Democritus, 460 to 370 BC, a Greek philosopher, proposed that all matter consisted of an infinite number of small particles. Today's atomic model. In 1808, John Dalton made the first modern atomic model that was widely accepted. He used scientific experiments to prove that atoms were real. Dalton believed that the atoms in an element are exactly the same size and weight. In his atomic model, Dalton suggested that atoms are similar in appearance to billiard balls. He also believed that atoms of two or more elements unite chemically to make compounds. By the end of the 1800s, it was generally accepted that matter is composed of atoms that combine to form molecules. In 1897, Joseph John Thomson proposed that atoms were spheres with negatively charged particles surrounded by an area of positively charged particles. He described the negatively charged particles as plums. Surrounded by a soup of positive material, he described as pudding. He called it the plum pudding model. Thomson also discovered the electron. In 1905, Albert Einstein wrote a paper that gave scientific evidence for the existence of atoms. Einstein also provided a way to count atoms by using an ordinary microscope. In 1911, Ernest Rutherford discovered the nucleus of the atom. He developed the first explanation of the structure of an atom. He found that most of the mass is located in the center of the atom, or the nucleus. He also found that the nucleus was positively charged, and that negatively charged electrons orbit the nucleus. In 1913, Niels Bohr proposed that electrons could circle a nucleus, moving in orbits called shells. As electrons move from one shell to another, they gain or lose energy. In the 1920s, Erwin Schrödinger and Werner Heisenberg proposed the electron cloud model for the atom. In the electron cloud model, the nucleus is the center of the atom. The cloud-like area represents where the electrons are likely to be found. Today, the electron cloud model is widely accepted. It is a good model of the atom, but it does not mean that this model will not change in the future as scientists learn new information. How is matter classified? Scientists classify matter by its characteristics. Matter is classified as elements, compounds, or mixtures. Some compounds can be acids or bases. Elements in matter. Can you believe that all matter around you is made of tiny atoms? Most things are made up of more than one type of atom. But there are some substances called elements with only one kind of atom. An element cannot be broken down into simpler substances by physical or chemical means. Some elements are gold, silver, aluminum, and silicon. Since they are made of only one kind of atom, elements are called pure substances. Chlorine is an element used to clean swimming pools. It is also used in bleach to wash clothes. Currently, there are about 112 different elements. All matter found in nature and space is made up of these elements. How can these 112 elements make up the great variety of matter? Elements can combine in many different ways to form all types of matter. The atoms of one element are not the same as the atoms of other elements. For example, the atoms of gold are not the same as the atoms of silver or the atoms of aluminum. Each element can be identified by the number of protons it has in the atom's nucleus. All matter that has 29 protons in its nucleus is copper. All matter with 13 protons in the nucleus is aluminum, and so on. An element's atoms have no electrical charge. Its atoms have the same number of protons and electrons. It means they have the same number of positive charges and negative charges. The overall charge of the atom is 0. Aluminum is a lightweight metal used to make drink and food cans. The element mercury is a metal. It is the only metal that is in liquid form at room temperature. Mercury is a toxic substance. Shorthand names for elements. Each element has a unique chemical symbol made of 1, 2, or 3 letters. The chemical symbol is usually the first letter of the element's name. If 2 elements have the same first letter, then another letter is added. Some element symbols come from their Greek or Latin names. For example, gold has Au as a symbol. It is from the Latin name aurum. Elements newly discovered have temporary 3-letter symbols, such as UUU, UUB, and UUQ. These letters correspond to the Latin name for the number of protons found in the nucleus, 111, 112, and 114, respectively. These chemical symbols are used by scientists throughout the world. This allows scientists to write formulas that others can understand. Grouping elements. Each element has a unique set of properties and a unique number of protons and electrons. Based on their properties, elements can be divided into 3 groups. They are metals, nonmetals, and metalloids. Metals are elements that are usually hard and can be hammered into sheets. They are good conductors of heat and electricity. They can be drawn into wires. Nonmetals are usually brittle, and they are poor conductors. They cannot be hammered into sheets or made into wires. Metalloids are elements with some properties of metals and some properties of nonmetals. Copper is a metal. Like other metals, it can conduct electricity and heat. Sulfur is a nonmetal. It is a soft, light substance that melts easily and doesn't conduct heat or electricity. Boron is a metalloid. It is a semiconductor. This means that it can conduct electricity only when certain elements are added to it. An organized table of elements. If you went to a grocery store and found all of its items in one large pile, it would be very difficult to find anything. There would be no aisles or shelves to separate the items. You would not know where to find the eggs or the bread. Scientists had a similar problem before they found a way to organize the elements. All the known elements have been organized in the periodic table. The periodic table is the work of Dmitri Mendeleev and J.L. Meyer. The different elements were arranged in order of increasing atomic weight, so that elements with similar chemical properties fell into the same group. There are different patterns to look at when studying the periodic table. When looking across the rows from left to right, all the elements are listed in order of increasing atomic number. The atomic number is the number of protons in the nucleus of an atom. Elements listed on the left side of the periodic table are metals. The nonmetals are listed on the right side of the table. Two series of elements are located at the bottom of the periodic table. They are the lanthanide and actinide series. Lanthanum is the first member of the lanthanide series. It has the atomic number 57, and it should follow barium in the periodic table. The atomic number is 26. This means an iron atom has 26 protons in its nucleus. The element symbol is made up of 1, 2, or 3 letters chosen to represent the element. Fe comes from ferrium, the Latin name for iron. The color shows that the element iron is a solid at room temperature. Actinium is the first member of the actinide series. It has the atomic number 89, and it should follow radium. The elements of these two series are only put at the bottom of the periodic table for convenience. If they were put directly into rows of the periodic table, the table would be very wide. The two series of elements are placed at the bottom so that the periodic table would fit nicely on one page. Helium has 2 protons in its nucleus. This element is located on the right side of the periodic table. It is a nonmetal. Beryllium has an atomic number of 4. It means this element has 4 protons in its nucleus. Beryllium is a metal because it is located on the left side of the table. The periodic table contains a lot of information about the elements. Each individual block from the periodic table contains different information about a particular element. Specialized periodic tables may even provide additional information about each element. The location of the element in the table also can tell you a lot about it. For example, elements found in the same vertical line or column have similar properties. The columns of a periodic table are called groups. Presently, there are 18 groups in the periodic table. Elements in group 16 have similar chemical properties, but some elements may be more similar than others. For example, polonium is more chemically similar to tellurium than to oxygen. Elements in groups 1 to 2 and 13 to 18 have similar chemical properties with other members of their groups. This means that oxygen and sulfur in group 16 have similar chemical properties. The only exception to the rule is hydrogen. It has a similar atomic structure as other elements in group 1, but hydrogen does not have similar chemical properties. A row on the periodic table is called a period. Unlike the elements in a group, elements in a period do not share similar properties. As you move across a period, elements adjacent to one another have similar mass, but the properties of elements change quite a bit. This is because you move from properties of a metal to properties of a nonmetal. Elements in period 4 have similar mass, but the properties of Ni to Kr are very different. Nickel is a metal, while krypton is a gas. What are mixtures and compounds? Elements combine in exact ratios to make compounds. Compounds do not have the same properties as the elements that make them. Substances which do not combine in exact ratios or undergo chemical changes form mixtures. These substances retain their own properties even when they are in a mixture. They can be separated by physical means. Building blocks of matter. Most matter in nature is not found as elements. It is found as compounds. A compound is a substance composed of 2 or more elements that are chemically combined. As a result, a new substance with different properties is formed. Sodium chloride is a common compound. You probably know it as table salt. Atoms of sodium and chlorine combine to form this common seasoning. But sodium's properties are very different from that of sodium chloride. Sodium chloride can be mixed into water to form salt water, but pure sodium reacts violently with water. When sodium is combined with water, you get a violent reaction. Sodium hydroxide and hydrogen gas are formed. A particle of a compound is called a molecule. These molecules are always made of the same ratio of elements. For example, a molecule of water contains one oxygen atom combined with two hydrogen atoms. It is always that 1:2 ratio of atoms for water. Compounds do not have the same properties as the elements that make them. Water has a very different characteristic than oxygen or hydrogen. Water is a liquid. The oxygen and hydrogen elements are gases. But when they both combine, you get water. Chemical formulas. Just as symbols are used for elements, scientists also use symbols for compounds. They use a chemical formula for each compound. A formula contains both the symbols for the elements and subscripts. A chemical symbol is listed out for every element that is present in a molecule of the compound. Then the subscripts tell you how many atoms of each element are present in the molecule. Let's look at the chemical formula for water, H2O. The formula shows that both hydrogen and oxygen elements are present in water. The subscript number 2 shows that 2 atoms of hydrogen combine with 1 atom of oxygen. The subscript always follows the chemical symbol of the element it refers to. The subscript 1 is never written out in a formula. If there is no subscript written, then there is only 1 atom of the element in the compound. Sucrose is a type of sugar used to sweeten iced tea. It has a chemical formula of C12H22O11. Sucrose is a compound with 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. Rust forms when iron reacts with the oxygen in air or water. It has a chemical formula of Fe2O3. It is a compound of 2 iron atoms and 3 oxygen atoms. Mixtures. A mixture is a combination of substances where the atoms are not chemically combined. Substances in a mixture keep their own properties. Take a pizza as an example. You may see olives, pepperoni, and other toppings. The toppings can be separated out easily. They are not chemically combined. Components of a mixture also do not have a defined ratio. 2 pizzas may not have the same amount of olives or pepperoni, but they are still pizzas. Separating mixtures. Mixtures can be easily separated. It is only difficult when the substances in the mixture are small in size. Let's separate a mixture of sugar, iron filings, and sand. Components in a mixture keep their own properties. The iron filings are magnetic, so remove them with a magnet. Next, separate the sugar from the sand. If you add water to the mixture, the sugar will dissolve. Pour the sugar-water-sand mixture through filter paper. The sand will collect on top of the filter paper. Finally, evaporate the water from the sugar water. You will have the solid sugar particles. Mixtures. Made of 2 or more substances. Do not have a chemical symbol or chemical formula. Each component keeps its individual properties. Not chemically combined. Can be separated by physical means. Compounds. Made of 2 or more elements. Have a chemical formula. Properties of a compound differ from the properties of elements that form it. Elements are chemically combined together. Can be broken down into simpler substances. Elements. Made of only one kind of atom. Have a chemical symbol. Called a pure substance. Cannot be divided into simpler substances. Solutions. It is easy to see the individual components in a pizza, but some mixtures look the same. These mixtures are solutions. A solution forms when one substance dissolves into another. The solute is the substance that is dissolved. The solvent is the substance in which the solute is dissolved. If you dissolve salt in water, the salt is the solute. The water is the solvent. Solutions can be solid, such as stainless steel, a solution of chromium, nickel, and iron. They can be liquid, like vinegar, a solution of water and acetic acid. They can be a gas, like air, a solution of nitrogen, oxygen, and other gases. The concentration of a solution is the amount of solute dissolved in a solvent. Solutions can be classified as being dilute or concentrated. Vinegar used in the kitchen is a dilute solution of acetic acid and water, while vinegar used in dill pickles is a concentrated solution. The maximum amount of solute that can be dissolved in a solvent at a particular temperature is called solubility. It is measured by the number of grams of solute per milliliter of solvent. The point of saturation is reached when no more solute can be dissolved in the solution. Any additional solute will settle at the bottom of the container. Acids and bases. You may think that acids are liquids that burn holes through everything, but not all acids are that strong. Many of the foods you eat contain acids. Oranges, lemons, pickles, soda, and milk are some examples. They contain weak acids. Even the cells in your body have weak acids to keep you healthy and alive. There are also some very strong acids. They are poisonous, and they can burn your skin. You should never touch an acid to see how strong it is. You can use an indicator. It is a compound that changes color in acids or bases. Litmus paper is an indicator that changes from blue to red when you dip it in an acid. Acids taste sour, but never taste a substance to test for the presence of acids. React strongly with some metals to form new compounds. Change litmus paper from blue to red. Many things you use contain bases. For example, shampoo, bleach, and soap have bases. Strong bases can react strongly just like acids can. These strong bases can also burn your skin. They are poisonous. Red litmus paper will turn blue when you dip it in a base. The pH scale. A pH scale tells you the strength of acids and bases. The scale ranges from 0 to 14. Acids have a pH between 0 and 7. As their pH increases, their strength decreases. Bases have a pH between 7 and 14. The strength of a base increases as the pH reaches closer to 14. The pH of 7 is neutral. Bases. Taste bitter, but never taste a substance to test for the presence of bases. Feel slippery. Change litmus paper from red to blue.